bro, hold on. We're trying to have a conversation.
It's just
Okay,
really funny to hear.
Castle, you do agree that we agreed earlier that gravity is mass independent. Things fall at a constant.
However, the further away you are from the source of gravity, the weaker the gravitational force is.
Okay.
Therefore, gravitational force.
But I'm talking about where we live. That's what I just said.
Yeah.
Okay, where we live, it's a constant of 9.8. Do we agree?
Yeah.
Okay, great. That's what I'm talking about. Okay, so if we have a container on Earth right now, this is on my screen. So this is how we observe gases to do. Equilibrium all size, and they take the shape of the container. Do we agree?
Mm-hmm.
If I had a balloon and a tire and I popped it, the air is going to fly out.
Mine's is using Wonderful.
Gravity...
I need the same thing. Okay, anyway, I'm going to go...
Bro, why you cutting me out, dude? Go ahead. Okay, if gravity was pulling gases down, it would act like this. There's no container on the globe model. So the force of gravity has to be strong enough to keep the gas molecules within the space of Earth without it leaving the atmosphere.
Some gases leave the atmosphere, though.
Okay, now here's the thing. There's no sum. Because if gravity is pulling all things down at the constant where we live, then they're not going to get into space. Because gravity does not depend on mass. Right?
Can I say something?
No, hold on. I'm talking to someone else.
Yeah, when you're done. All
right, my bad. Yeah, go ahead. All right, so go ahead, Castle. Tell me why this doesn't work.
No, I want him to say what he's going to say first.
But I don't want to get off topic because we switch a bunch of topics. So we were talking about the sun thing earlier, and you couldn't disprove that, so we switched to this. But I want to stick to this target because you guys keep saying I'm wrong. So if gravity was pulling gas molecules down and it can't hold it here, how's it going to hold it the further you get up in the atmosphere when gravity's weaker?
Because you have the molecules in the upper atmosphere pressing down on the other molecules because, pressure.
Okay, now, you just said that the gas molecules that are above are pushing the winds down below. What is holding the gas molecules that are above to Earth?
Gravity.
Okay, gravity. If gravity is pulling it down, what you just described was a liquid. If I have a container with, let's just say, water, syrup, and oil, they're going to fall and stack. That's what liquids do. With gases, if I have a container with 3 different gases, 3 different densities, let's say helium, air, and sulfuric hexide, they're going to take the shape of the container and separate. You describe the properties of a liquid, not gas. Gases don't fall and stack up on top of each other.
They do, though, because you have the particles of gas hitting each other, pushing each other up and down, up and down.
Okay, let me show you. Hold on. Okay, so here's how liquids work.
It's the same as liquids. All of them mix.
Let me show you the difference between liquids and a gas. If this is a container with liquids, again, pull me up if I'm wrong. If this is a container with liquids and this is a container with gases, and let's just say we got 3 different densities, right? So the bottom, oil, whatever, it doesn't matter. And we got water. Hold on. Water in the middle, right? They're going to fall and stack up on top of each other. And then we got, syrup at the top. Okay. They're going to fall and stack. Now with gases, how they would work is gases take the shape of the container like we agreed earlier. So gases, it'd be like this. These would be at the top. These would be in the middle, right? And then these would be at the bottom. So the clear difference between a gas and a liquid is that liquids fall and stack. Gases don't.
So that's on a small scale. On a large scale, however, I'll quickly show you on this. Let me get... Where is it? Why is paint not coming up on my thing? 1 second. Oh, there it is. Taking a moment. Right, paint, go live. So, on a small scale, yes, that's how it would work. But on a large scale, let's say this is like the entire atmosphere of Earth right here, and here is the outer layer up there. And let's say this is the surface. I'm just doing this as a shape of a container. So up here, we've got a small amount of particles. And they have a small amount of gravitational force pushing them down. And over here, we've got a lot of particles. And of course, all the particles are mixed together. So you've got a mixture of nitrogen, oxygen, argon, all of those lovely gases, right?
Mm-hmm.
All the way down here. And as you go up, it gets less dense. Now, this is because of temperature and gravity. So this gets less and less and less and less dense. Now, the reason why it doesn't drift off, first off, gravity. Now, the reason why it doesn't all come to the bottom is because of pressure pushing these ones back up by colliding with these ones. So these will collide with each other, keeping them in a very uneasy equilibrium, just as these would collide with each other uneasy equilibrium, and eventually you get it so it's more dense down here because there is, well, more collisions.
All right, I get you. All right, look at my screen now. Okay, I screenshotted your analogy. Okay, the problem with this is the gas is up here. Like I said, if gravity is not pulling, if gravity cannot keep gas, like for example, right? If we have a gas molecule right here, we have a constant is pulling it down at 9 meters per second squared. So, and all the air is, all the oxygen, all the gases are produced down here. So, if gravity is not strong enough to hold gases down here, if this gas molecule moves upwards, gravity is weaker. It's not going to hold whatchamacallit. Gravity is not, if gases can escape the 9.8 meters per second squared that they fall where we live, they're going to go up, and when they go up, they're going to move to space. There can't just be gases floating up here because of gravity. Okay, now there's only two options. It's either they're up there because they're stacked up on top of each other, or they're up here, they're just floating up there, which doesn't make any sense because if gravity can't hold it down, then it's not going to stay on Earth.
Do you understand acceleration? I need to just check this first because I think this is where you're misunderstanding me.
Exponential distance over time?
So, acceleration.
Rate of change of acceleration, I mean.
Yeah. So, acceleration. So, at the surface, it accelerates towards the Earth at 9.81. And as you go up, the acceleration decreases, but it's still accelerating you towards the Earth.
They keep 90% of the gravity.
The escape velocity to leave the Earth is what? Escape velocity to leave the Earth is 11.186 kilometers per second. For a particle on the surface of the Earth to leave the atmosphere, it would have to go at 11.186 kilometers per second, which is incredibly fast. So you will never get a particle able to drift that high without some kind of other aid or being there for thousands, hundreds of thousands.
Do you agree that all gas molecules, when gas molecules bounce out of the container, do you agree that their collisions are perfectly elastic and they lose no energy?
I'm.
You can Google it. Just Google it.
They're theoretically meant to, but no, they're not.
So you think that they're going to lose energy?
They will eventually lose energy due to sound and thermal.
What? How does that? What?
Okay, rub your hands together real quick. Rub your hands together. Are they getting warm?
Yeah.
Imagine that with gases, much less dense, but the same principle applies. You're losing energy.
That's because the energy gets transferred to. Okay, hold on.
Exactly. Kinetic energy is turned into heat energy.
So you're saying the energy of the gas molecules colliding inside the container would transfer to the container?
Yeah, that's how. Well, okay, let's do this. So let's say you have a really, really dense amount of gas in a container, and you have a basically empty container. The really, really dense amount of gas container is actually going to be slightly warmer. Very, very slightly. Because every time the collision happens, if you punch your desk really hard, it's going to warm up the desk a tiny amount. If you do it repeatedly, the desk will warm up enough, it will eventually catch fire.
I agree.
It's like the entire thing of slapping the chicken, like 300,000 times, it'll eventually cook.
Oh yeah.
Yeah.
Or you have to slap it like really, really hard, really fast.
Yeah, I agree. Okay, so my point still is, how are the gas molecules staying up here if they're outside of the constant? If they're not being pulled down at 9.8?
Let's say they're being pulled down at 2. Okay?
No. Up where the exosphere is, they keep 90% of their gravity.
Okay, let's say it's being pulled down by 1 then.
1 what?
1 meter per second. Squared. Sorry. Squared. Forgot the squared part.
No, it's not that though. In this area where the top of the atmosphere is, they keep 90% of their gravity. So it'd be like 8.6.
Of gravity.
Huh?
You say they keep 90% of the gravity.
Yeah.
So it'll be 8. Right, okay, so it's 8.6. There's less things to collide with.
Okay, what does collisions have to do with it going up or down?
When it collides with something, it transfers momentum.
Okay, if the gas molecules are here and they're bouncing towards each other, this is not explaining at all why they're not going down or up.
Okay. No. So it's because you're doing such a small scale system. Add in, 50 million gas particles. They'll all be colliding with each other constantly, all moving around. So that particle collides with one, leads to the other, another.
Here's what makes no sense. Hold on, look, Brett. If I had a bunch, I'm not going to draw 50 million, but if I had literally like a bunch of gas molecules with nothing containing them, they're not
Okay,
going to hit
wait.
each. They're not going to hit each other and stay in the same area. Okay, and where's gravity pulling them? Down here, not towards each other. Right. So my point still stands that the gas molecules up there are not strong enough to be held to Earth because down here, gas molecules aren't pulled by gravity. So up there, gas molecules cannot stay stuck to the spinning ball.
But this
Okay.
brings back the entire concept of. Sorry, I'll let you speak in a second. Sorry, I just want to say this. This brings back the entire concept of having a vacuum when you move a particle out the way because there's now an empty space there.
Dude, vacuums don't suck.
Hey, wait.
What's your question, bro? What's up?
Okay, so you're saying that? Are you? Sorry, let me just. Can you restate what you're trying to argue here?
Okay, my point is that if gravity existed, then it'd pull any container with gases, gravity would pull it down if it falls.
Yeah, and it is being pulled down, right?
Okay, so my question is.
So here's my thought. Gas is throughout like the air dense, full of stuff, right?
Uh-huh.
Like that's why we have an atmosphere. So like think about it, of all those particles in the air, it's like water. It's like their atmosphere is a big ocean that extends up past our planet, and the molecules can't go any further down. It's because it's filled with stuff, and the amount of gravity isn't strong enough to make it denser. Like that's why when you have bigger planets with denser atmospheres with more densely packed gas closer to the planet.
If it's not strong enough to pull it down to the Earth, then how is it stuck to the Earth while it's falling?
No. I mean like it's not like gravity isn't strong enough to pull a piece of like driftwood that's floating across the water down into underneath the water. Like unless if the gravity was stronger, then it would be able to pull the floaty wood down. It's kind of like,
but that's the difference between liquid and gas. So liquids fall and stack up on top of each other. Gases don't. The gas at the top. Let's just say the gas is at the top most of the atmosphere.
yeah.
Okay. You're claiming that you're claiming that gravity is keeping it in orbit. It's keeping it stuck to Earth, right?
Yeah.
Okay. So if gravity is pulling the gas molecule towards the Earth,
Yeah.
why is it not going towards the Earth?
Because it is.
It is.
It is.
Okay, if the gas molecules at the top of the atmosphere is
Yeah.
going down towards the Earth,
Yeah.
what this means is if I have a container with gases anywhere, exosphere, thermosphere, stratosphere, doesn't matter, wherever I am, I should observe that the gas molecule is pulled down, just like you guys said. But inside of right, but that's the problem. Inside of a container with gases, the gas molecules do not have a pressure gradient. They don't fall to the bottom. They don't stack up on top of each other. That's what liquids do.
I'm
That's
sorry.
my point.
So you're saying like a container, like on what scale? Like a small like plastic box you have at your house, or like
Anything.
okay?
The best scale is down here on Earth. Gravity can't pull gases and they can't keep them in a container down here on Earth. It's not going to do it in the exosphere.
Yeah.
Sorry.
Okay. So
I don't agree it's the best way of doing it because you are comparing tomatoes to oranges right now. Because gravity changes for the atmosphere. Meanwhile, for your box in your house, it does not change gravity. Therefore, it's not a fair test.
No, the reason I said down here is because gravity is the strongest. If it's not holding gases to the floor down here, it's not going to do it up in space.
But there's less.
Okay, can we switch topics now? Because I want like everybody else.
Sure. Yeah,
Okay.
I don't necessarily have but that wasn't my original question. My original question was like, okay, so you're saying that gravity doesn't exist?
Yeah.
this.
Because I guess that would be the biggest thing about. Okay.
I mean, the thing is, they teach in causal physics that there's other electric forces stronger than gravity that dictate why things fall where we live.
Yeah,
Gravity-
You have four forces, but gravity isn't this. Sorry.
So in that sense, like the idea that like a flat Earth, like gravity wouldn't really exist because it would get pulled into a sphere shape, right?
Yeah, we gotta pull towards the center. Okay, hold on. What about okay, let's talk about stars, right? So
Oh, yes.
I know- as your specialty? Okay, great. Do you do like astronomy or anything like that?
Yeah, I'm going to be doing a degree in this sort of stuff.
Okay. So do you study cameras or anything like that?
Not Cambridge, no.
No,
Not that.
cameras.
Oh, cameras.
Okay, so basically, I'm gonna explain how stars work on the flat Earth model, and then you can tell me why you think is wrong.
Okay.
Okay, so on the flat Earth model, this is the Earth, and above the Earth is this dome. Matter of fact, let's go with the dome. I want to talk about that first, and then I got to start.
Dome.
Oh yeah, the Simpsons talked about it. Okay, there's a dome above the Earth, and we can observe the dome. Hold on. Let me pull up a video. Okay, when you shine light under a reflective surface like this, you have a light source under a reflective surface, the light diverges just like this. And this is seen in real life. This is Antarctica. You can see light reflecting off the dome. Here's another video of light reflecting off the dome. You can Google these. These are called sundogs.
Albedo effect.
What happened?
Albedo effect. It's when light reflects off a white surface.
Light reflects. What surface is this reflecting off of?
Snow.
Well, the lens
The snow's on the floor.
Photos so far have been on snow or ice.
Yeah, because on the flat Earth model, that's explained because it's only in the outer edges of the world.
Exactly, the albedo effect.
Right, but the snow's on the floor.
Yeah, and it reflects off the floor.
Dude,
And
look,
it's such a large area that it all reflects off.
This
Until
is-
the Earth is curved, it then curves the light.
Okay. Doesn't make any sense because it's not going. The curvature is not going down. It's a circle. It's a straight circle around this dude's head. It's a dome. Like, and there's even like a rainbow up top here too. Like, hold on. That's the top corner of the dome. Snow does not make that effect.
Okay, has anyone physically touched this dome then? Is there any
Yes.
videos of that?
Yes. You want to see it?
Oh, yes, please.
I got you. All right. So
Yeah,
Here-
videos.
Yeah, not gonna lie, I
There's no
touched it
evidence
yesterday.
that these videos
Okay.
I want to see someone touching the dome. I want to see what happens to their hand. I want to see if
Okay.
it like, dissolves or...
no, their hand. Okay. I'll get to why. Okay. First, let me show you a video of a rocket hitting the dome. All right. You gotta turn the stream volume up.
Ooh, nice rocket design, actually. Didn't too much, though.
I'm gonna skip to where it hits the dome. All right. Listen.
So where's this being launched from?
Come on. Okay, it's hit the dome. I'll bring up the YouTube video in a second. Okay, so I'll replay it. The rocket's spinning and it hits the dome. All right, and then it's going to start falling back down to Earth. I get the
So
location.
it hits the dome and nothing happens. It just comes back down.
Yeah, it's going to start falling. Hold on, give me a second.
So what happens to the energy?
I don't know the properties of the firmament.
Energy
But obviously,
must be conserved. That is a universal law that underlines everything.
the energy not conserved. You mean
Energy must be conserved. So if it hit a dome, where did the energy go?
to the dome?
And what happened? Why is the rocket not crumpled? Why did the rocket not get destroyed when it hit said dome?
I don't know the properties of the dome.
Because
But
if it hit
all we
the
know
dome,
is that-
it instantaneously stopped, right? What happened
Okay.
to all of that kinetic energy it had? Because if I punch a wall really, really hard, it will break my hand. But somehow the rocket suffered no
But
damage.
also, Castle, if you punch a ball really hard, what's gonna happen? Your hand's going to stop. This hit something,
Oh, my hand will stop. Yeah, just like the rocket will stop. But my hand,
right? Because it hit something.
The impact of
the hand's gonna absorb the force.
yeah, my hand will absorb the force and it will deform. It will break my knuckles. So why is the rocket?
When you
okay? Why is
when
that
you
actually a
punch
video?
when you punch like rubber or something, rubber absorbs it. I don't know the properties.
of a rocket.
It's
You
an
see-
No,
elastic.
I'm not saying the dome's rubber. I'm saying that there's properties that can absorb energy. Okay,
So
I don't know the
absorb
properties of
all
the dome.
energy, and the rocket is perfectly intact when it hit this surface.
Okay, let's hold
There's
on.
no solid value.
Okay, hold on. Listen, you're avoiding like